Hello learners, welcome to this tutorial on basics of analog to digital converter in microcontrollers. Analog to digital converters play a very vital role in any embedded system because an embedded system needs to work with real-time inputs. So the inputs are obtained through a sensing elements. So the sensors are nothing but a transducer which can convert one form of energy into another form. So when an embedded system is deployed in certain situation, it needs to take some real-time inputs. So that is done with the help of a sensing. So sensors can be of two types. One is analog sensor, another one is digital sensor. So analog sensors gives the output in terms of a continuous signal, whereas a digital sensor, it gives a digital data. So if we are interfacing a digital sensor with your microcontroller, then we can get the data as it is and we can do the processing. But most of the sensors available worldwide are analog in nature. So analog in the sense, any physical quantity measured, it will be converted into a continuous analog signal. So this signal needs to be converted into a digital data before processing by your microprocessor or microcontroller. So in order to do that, we require an ADC. So ADC is an analog to digital converter. So it takes an analog input and it converts it into a digital value. So the applications where it is used in the sense, it is used in automation circuits for industrial automation, robotics, medical electronics, home automation, etc. And also sensing and monitoring circuits also, it is widely used. Mostly ADC in a microcontroller comes in different formats like 8-bit, 10-bit, 12-bit, and generally we can say it as a n-bit ADC. What does this 8-bit, 10-bit, 12-bit or n-bit represent? So it represents the digital value which we get after the conversion process. It takes an analog input, it gives a digital value. So how many bits we use to represent this digital value is nothing but the n-bit value. Usually in a microcontroller, the ADCs are implemented using a successive approximation type ADC. So here I have shown an block diagram representation of a successive approximation ADC. So here it takes an input signal, sensor input signal, and first block we have a sample and hold circuit. So this analog value is sampled and it is retained for certain time period. And this input voltage is compared with the voltage of your digital to analog converter. So digital to analog converter is a reverse process of your ADC. So ADC, it converts analog value to a digital value, whereas digital to analog converter, it converts your digital value into an analog value. So this DAC, it produces an output in relation to its digital data. So this digital data is obtained from a SAR register. SAR register is a successive approximation register which has a combination of binary values. For example, if I take a 8-bit value, so then it starts with 8 zeros, then it increases to a maximum value of 8 ones. So altogether we will have 2 power n combination. So 2 power n is 2 power 8 combination. So 2 power 8 means we will get 256 combination of digital data will be present in this SAR register in case of a 8-bit SAR. If I have a 10-bit SAR, then it starts with 10 zeros and it ends at 10 ones. So in between I have about 1023 such values because 2 power 10 is nothing but 1024. Since it starts with the 0, we take a count one value less than that of 1024. So altogether I have 1024 entries in a SAR register. It starts with 0 and it ends at 1023. So this digital value will be fed as an input to your DAC. So first let us assume that some value is given by this SAR register and the DAC produces a corresponding output voltage. And this voltage is compared with your input voltage. If there is a mismatch, then the next entry in the SAR register will be given as an input to your DAC. So this scenario happens until the comparator produces a equal result. Once the comparator produces a equal of input voltage with the DAC voltage, then the binary bit pattern will be freezed. Then that binary bit pattern will be obtained as a digital data for the corresponding input. So that is how this successive approximation ADC works. So if you look at this successive approximation ADC, in that you have a DAC, and this DAC requires a reference voltage. So this reference voltage can be a IC supply voltage, which is VCC, or it can be any external reference voltage which can be given by the programmer, or we can also have internally generated reference voltages. And one of the important parameter of your ADC is its resolution. What is resolution? Resolution is nothing but the smallest voltage change represented as a proper digital output pattern. So for example, first let us try to compute the resolution. So resolution depends upon your reference voltage and the number of bit of ADC. So if I take a reference voltage of 5 volt and n value takes a value of 10, then in that case the resolution is computed by this formula V reference divided by 2 power n minus 1. So V reference I have represented it as 5000 millivolt, which is equivalent to 5 volt, and 2 power 10 minus 1. So 2 power 10 is 1024, 1024 minus 1 is 1023. So what we are doing is 5000 millivolt divided by 1023. So that gives about 4.88 millivolt as a resolution. So what it represents, if my analog input is 0 volt, then the binary bit pattern which we get is 10 zeros. Then the next binary bit pattern is your 9 zeros and 1 in the LSB part. So this value will be obtained if I have an analog input voltage of 4.88 millivolt. In between values, for example, if I take 2.44 millivolt, then I don't have a proper binary bit pattern for that input voltage. Either I have to round it off to your earlier 10 zeros or 9 zeros 1. So here we will have something like a round off error will be there. So this is what we say it as a resolution. So this is the smallest voltage change which is represented in a proper binary bit pattern. So if I have a voltage less than this, then I need to do an approximation. I might not get a proper binary bit pattern. So it will have certain errors. So that is what we define as a resolution. So if I want to change the resolution, if I want to measure 2.44 millivolt also, in that case what I can do, I have two options. One is either I can change the reference voltage or I can change the n bit. So n bit, if I want to change, then I have to change the IC, because a certain microcontroller will come with a 8-bit ADC or 10-bit ADC or 12-bit ADC. If I want to change the n bit, then I have to change the microcontroller itself. So better solution is to change the reference voltage. If I change the reference voltage, for example, if I take a 2.5 volt as a reference voltage, that I have represented it as 2500 millivolt, and n bit, n I have taken it as a 10. Then when I do the computation, 2500 millivolt divided by 2 power 10 minus 1, it comes about to be 2.44 millivolt. In that case, what happens? The first binary value is 10 zeros for 0, and the next binary value 901 is for your resolution of 2.44 millivolt. So here we can have a higher resolution. Even a smaller voltage is represented properly in the binary bit pattern. So that is what happens when I change the resolution. If I want a higher resolution, then it is better to change the reference voltage for your ADC. So if I change the n bit, also we can get different resolutions. So one example I have given here is, I have taken a reference voltage of 5 volt and n bit to be 8. In that case, 5 volt divided by 2 power 8 minus 1, which comes about to be 19.6 millivolt. So here the smallest voltage change which can be represented as a proper binary bit pattern is 19.6 millivolt. So as I keep on doing it from 0 volt, and I increase in number of steps, quantization steps. Once I reach 1023, in case of a 10-bit ADC, I will reach 10 ones as a digital data. So this is the binary representation for different input voltages for a resolution of 4.88 millivolt. So one more important thing is, depending upon the reference voltage, our input voltage swing will be decided. So if our reference voltage is 5 volt, then the input can swing between 0 to 5 volt. If the reference voltage is 2.5 volt, then the input can swing only between 0 to 2.5 volt. So the reference voltage determines the resolution, and also it determines the input swing for your input voltage swing of your sensor. So this is the basics of your ADC, which is available in your microcontrollers. In the subsequent videos, we will look at the programming part, configuring part of your ADC in microcontroller. Thanks for watching this video. Please subscribe for more technical learning. Thank you.